The Big Bang had no singularity. See, back in the 90s, Stephen Hawking and James Hartle proposed a radical alternative to the singularity, and the beginning of time. It's called the no-boundary proposal, and it might be one of the most controversial ideas in quantum cosmology. Let me set the stage. The universe is expanding, and, as far as we can tell, it was expanding in the past too. As you wind the clock back, the universe gets smaller and smaller until, if you trust Einstein, the universe reaches a size of zero, a singularity, a place where the curvature of spacetime is infinite. The trouble is, never in the history of science has a singularity been linked to physical reality. A singularity is a sign that a classical, meaning non-quantum theory, is breaking down. As an example, under a classical view of electromagnetism, when a positive and negative charge get close enough, the attractive force goes to infinity, as does the kinetic energy of the system. This is another kind of singularity, and it signals a breakdown of Maxwell's electromagnetism. To resolve the singularity, the electron was smeared out by quantum electrodynamics, so even when an electron overlaps a positive charge, all of the predictions remain finite. Analogously, it's reasonable to think that a theory of quantum gravity could resolve the Big Bang singularity by smearing the geometry out there. It just gets really weird when we're talking about spacetime itself behaving this way. In quantum theories, we typically compute transition probabilities. You have two distinct states at different times, an initial state and a final state, and then you ask how likely is it to go from one state to the other. The trouble is, a Big Bang singularity is not a well-defined initial state because of all of the infinities that abound. And one could instead specify some arbitrary initial state, also known as a spacetime boundary, but that typically means that something external, something prior, caused that particular initial state. And that just pushes the goalposts back another step. But what if there was no initial state? Think of the traditional picture of the Big Bang, a pointy tip at the Big Bang and a cone expanding outward from it. That tip, the moment of the Big Bang, is a boundary. You could get rid of the singularity by opening up that pointy tip, but then you'd have to specify the conditions at the opened edges. But what if that tip was rounded off instead? Then there'd be no boundary at all, in the same way that the South Pole isn't the edge of the Earth. This way, no prior externally provided information is required, and that's exactly what Hartle and Hawking proposed. But here's the trouble, there just isn't a well-defined spacetime that rounds off like that. The only way to get a sort of boundaryless spacetime is to treat time as complex. As you wind the clock back sufficiently far, regular time gives way to imaginary time, the square root of -1. And weirdly enough, imaginary time behaves like regular space, except one of the spatial dimensions is special. So they went with it, and it worked. In this picture, the early universe is essentially completely spatial, and described necessarily with quantum gravity. And while there is a notion of complex time, the way that we think about causality completely breaks down in this phase of the universe. And it's really hard to say anything about what the universe was like, because its geometry is just not classical. But what's true is that if we assume this non-boundary is the initial state, then the probability of transition to a classically evolving universe is high. At some point, imaginary time undergoes a transition to real time, and off we go. In this proposal, this transition happens at a particular well-defined size, roughly the inverse of the primordial Hubble constant. And that means that asking what happened before the universe was this size doesn't really mean much. Time as we know it didn't exist, and causality didn't behave in the normal way. So even though, under this proposal, the universe comes from nothing, there's no need for an external cause. It's entirely self-contained and self-consistent. And certainly, there's no Big Bang singularity. Of course, maybe their proposal is wrong. It turns out that quantum gravity is hard, and this is still an active area of investigation. The original proposal makes some assumptions about the universe that we now know aren't true, but the idea does seem to be salvageable even if the mechanism gets more complex.